we call it prosthetic group. If the non-protein parts is loosely attached to substrate, we gave them a name. We call it coenzyme. Okay. Now, coenzyme, I gave you an example. Vitamin B is a coenzyme for FAD synthesis. Okay, so that's all the concept. And we also call this part called the cofactor. And if you combine these two, we call it hollow enzyme. Now I gave you an example. RNA polymerase. What is that? Alpha, beta, beta prime, and omega. This is coenzyme. And sigma is a cofactor. And this combined together is a hollow enzyme. Okay, we'll mention this again. Okay. Now we move on to another question. How do we evaluate an enzyme? How do we know this enzyme is good or not? This comes up something else. We have a formula. Okay, we always do. Velocity, that's V. Right here, substrate concentration. And always remember, the substrate and the enzyme reaction is always kind of like a bacterial growth curve. Do you feel it's similar? Later on will become flat. Which means it's going to be saturated. Okay? What do we care about? We care about V max, and we care about another thing right here. To have V max, we talk about this Km value. Okay, so first of all, how we evaluate the action of the enzyme? At the beginning, the substrate, there's enzymes that reacted. With the increasing of the substrate concentration, the reaction happens very quickly. Okay, they happen all the way. However, later on, it will become saturated. Therefore, we have comes from the concept of the Vmax. That means the rate of products formation at the saturated enzyme with substrates, and it happens as soon as possible. Which means that if I have enough substrate and I have a saturated enzyme, how fast it will generate a product? That is called the Vmax. Now, we think using Vmax to describe it is not really enough. Therefore, we come with a Km value. The Km can be calculated as Vmax multiplied by S divided by, sorry, that's a V. Km added by S. Now, what this means, maximum reaction speed. Now, why we use this one can be to evaluate, because the smaller the Km value, the more closely attached of enzyme with the substrate. Okay, that's why we use this Km value to evaluate. If you see a smaller one, which means it's more closely attached. Okay, so that's how we find it. Now, there is a lots of the model to describe the reaction between substrate and the enzyme. The first one is called lock key model. The enzyme like a lock, substrate like a key. You combine, you react it, like you use key to open a door. This is a simple. Then based on this model, people find what will be the impacts to affect the enzyme. Now, of course, we know temperature. We know pH. There will be effective impacts of the enzyme. Why? Because enzyme, the major component is a protein. So the temperature cannot be too high. Otherwise, the protein will be denatured, so lose the function. The pH cannot be too acid or too alkaline. It will be denature the protein. And also the substrate level concentration. The substrate concentration, we talk about the Km value. And there's something else we want to say. This is basically is true, but there is some exception for bacteria. Taq enzyme. This enzyme is highly resistant to temperature, high temperature. That's why it is used in the PCR reaction, polymerase chain reaction. Why? Because the Taq enzyme is isolated from thermophiles or hyperthermophiles, kind of like the bacteria, like geobacillus, which means the bacteria is already be heat resistant. Okay? So that's something I want to mention. Now the last part, how we regulate the enzyme. The regulator enzyme, there is several ways to do. The regulation, the first one we call it competitive. So what is competitive? Okay. I had a substrate. I had an enzyme like that. Okay, this enzyme. I had a substrate. I have a competitor. A competitor, the morphology very similar to a substrate. This is going to be a competitor. And the substrate, their morphology is the same or very similar. So instead of the substrate to react it with the enzyme or attach it with the enzyme, this guy could go here to block the substrate with the enzyme. So for example, PABA. This is a metabolic precursor for bacteria to generate folic acids. Okay, it is important. I have a sulfur drug. The morphology or the chemical structure of the sulfur drug to PABA, beta benzoates, okay, by the way, beta benzoates, is very similar. So I could block this happening. That's why it is. Looks like this. Sulfur laminide, which is a sulfur drug, compared to PABA, beta benzoate, their topo looks very similar. So instead of PABA with enzyme reacted, the sulfur drug will be reacted with the enzyme. So the folic acids will be prevented. And the bacteria must be synthesis folic acids. Otherwise, they will be dying. Lots of the bacteria. Now, the question is the sulfur drug safe for the human being? Yes. Because the human being will not create folic acids by itself. They have to take it from the diets or the other resources. So remember, if you're a pregnant woman, they will tell you, you need to daily take 400 milligram per day, the capsule of the folic acids with multivitamin. Okay? That's why sulfur drug is safe to be used, because the human being will not generate the folic acids. So this is an example for competitive inhibition. Okay, what is non-competitive inhibition? We call it allosteric reaction or inhibition. So what happened then? This is a substrate. Okay, this is the enzyme. I'm not going to find something. Sorry. This is the enzyme. This is the substrate. I'm not going to be to find something competitive, to grab the same location of the reaction. I'm going to do something attacking here. Okay, then your morphology going to be changing. You not become this at all. You may become like this. So the substrate cannot attach it, cannot react it. And this is called allosteric reaction. Allosteric reaction, a good example is lactose operant. And we will mention in the next couple of weeks. Another example is heavy metal, like mercury. Those heavy metals usually will be killing the bacteria. They are going through allosteric regulation, and it's non-irreversible. Okay? The last one we need to know. Bacteria in their shorter period of time in life, they have something to control its natural rate, which means called end product feedback inhibition. So if they generate too much end products, they could go back to change the morphology of the enzyme, then to block the following biochemical reaction. Because they think it's too many end products, we have to stop it. Because that's economical ways they can use. And that's called feedback inhibition. The feedback inhibition could be reacted to the final substrate products, or they could be reacted to the intermediate products. We also call it a metabolic precursor. So just want to let you know, and the mechanism behind this is allosteric inhibitor. Lactose operant is another example. And the tryptophan operant is another example. We'll mention this real quick. Okay, so here is end up with this section. The key here is electron transport chain and two-half reaction, and your understanding about that. And also biochemical reaction, the chemosmosis theory is important here. Okay.